Hello, let's start one more lecture session on multivariate integration. In the last lecture session, we have seen surface integrals of vector fields. Today, we will see the Gauss's divergence theorem, which relates such surface integrals with volume integrals. Let us see the statement now. So let V be a closed bounded region in space whose boundary is a piecewise smooth closed surface S that has orientation pointing out of V. And let f xyz is given by pxyz, qxyz, rxyz be a vector field whose components have continuous partial derivatives in V. Then the statement of the Gauss's divergence theorem is like this, that the volume integral divergence f dv over the volume V is equal to the surface integral f dot n ds over the surface S. Here, this n is the outward pointing unit normal at each point on the boundary S. Now, very often, this n ds is also just written as ds. So let us now see some important facts about this theorem. So what we have observed just now, that the divergence theorem relates surface integrals of vector fields to volume integrals. Now, as we look into a physical interpretation of the divergence theorem, we may see that the left-hand side of the equation represents the totality of the sources in the volume V, and the right-hand side represents the total flow across the boundary S. And lastly, let us note the form of the divergence theorem in Cartesian coordinates. See that the volume integral divergence f dv, as if is having the components pqr, will be now given as del p del x plus del q del y plus del r del z, and the volume element in Cartesian coordinates is dx dy dz. And the surface integral f dot n ds may be written as p dy dz plus q dx dz plus r dx dy over the surface S. Now, having known the Cartesian form of this divergence theorem, we can now obtain a very important formula for obtaining the volume of the solid V. So, how this is obtained? If we take the situation P equal to X, Q equal to Y and R equal to Z, see that each of these quantities del P del X, del Q del Y, del R del Z all become 1. So therefore this expression gives us just 3. So now the volume integral dx dy dz over this volume V will be given by 1/3 the surface integral x dy dz plus y dx dz plus z dx dy. And of course, we remember that this volume integral or triple integral, whatever we call now, triple integral dx dy dz over this volume V gives nothing but volume of this entire region or the entire solid V. Let us now proceed to see examples on Gauss's divergence theorem. So use the Gauss's divergence theorem to evaluate the surface integral f dot ds over S, where the vector field F is given by the components x, y, z, and S is the surface of the solid bounded by the cylinder x squared plus y squared equal to a square and the planes z equal to -1 and +1. So let us draw the region and the surface. So this is a cylinder with radius a bounded by the planes z equal to -1 to z equal to +1. Now, as we proceed to evaluate the surface integral using the divergence theorem, so we convert the surface integral into the volume integral. So now del dot f, as f is having the components x, y, z, this is just del del x of x plus del del y of y plus del del z of z. So this expression gives us nothing but 1 plus 1 plus 1, that is 3. So we get 3 times this triple integral dx dy dz over the volume V. So we now proceed to evaluate this triple integral. And for that we need to find out the limits of xyz. So as we look into this region, it's very easy. We can easily see that z varies from the lower surface z equal to -1 to the upper surface z equal to +1. And as we would like to find the limits of x and y, we see that the projection of this cylindrical region over the xy plane is nothing but a circle of radius a. So we can now again easily find the limits of x and y. But because this region on the xy plane is a circle, it will be convenient to transform into polar coordinates. So let us now proceed to evaluate this triple integral. So this is dz, we are integrating from -1 to +1, and dx dy, as we transform to polar coordinates, we know that this is replaced always by r dr d theta. So we have this r dr over here, and this is the integral with respect to theta. And the region is a circle of radius a, so of course r varies from 0 to a and theta varies from 0 to 2 pi. So we can easily evaluate this integral now. So we get 3 times. Now this -1 to 1 dz, this gives us 2. This integral 0 to 2 pi d theta gives us 2 pi. And as we integrate this, we get r square by 2. Limits are from 0 to a. So finally, our answer is 6 pi a square. Let us now take one more example, but now we would like to verify the divergence theorem. So the question here is, verify the divergence theorem for the vector field f of xyz given by the components 2x square y, xz square, 4yz taken over the rectangular parallelepiped bounded by the planes x equal to 0, x equal to 1, y equal to 0, y equal to 2, z equal to 0, z equal to 3. So let's first draw the figure of the rectangular parallelepiped. This is here. So we see that it extends along the x direction from 0 to 1, along the y direction from 0 to 2, and along the z direction from 0 to 3. So as we have to verify the divergence theorem, which we have just now seen that it's given like this, that the volume integral divergence f dv over v is equal to the surface integral f dot n ds over s. So we have to evaluate actually both now the volume integral as well as the surface integral and check that whether the answers match. So let us first try to find out the volume integral. So del dot f dv, we write down the components of f, which is 2x square y, xz square, 4yz. So as we calculate this partial derivatives, we get this as 4xy. This term is 0 and this gives us 4y. So this is essentially 4x plus 1y. And because the region is a rectangular parallelepiped, we can easily put the limits. We see that x extends from 0 to 1, y varies from 0 to 2, and z varies from 0 to 3. So we now proceed to evaluate this triple integral. So as we proceed to do that, we see that here we integrate this with respect to z. So x and y are of course constant. So we just have x plus 1 y z. Limits are from z equal to 0 to 3. So as we put the limit of z, this will just give us a 3. So we have 12 over here, 0 to 1 dx and 0 to 2 x plus 1 y dy. So as we integrate with respect to y, we get x plus 1 y square by 2. We will put the limits from 0 to 2 and then we have to integrate with respect to x from 0 to 1. So as we put the limits of y over here, this y square by 2 will give us just a 2. So 12 into 2 we get a 24 outside And now x plus 1 dx. As we integrate, this is x squared by 2 plus x. And we put the limits from 0 to 1. So finally the answer is 36. Now the next step is to evaluate the surface integral. But as we proceed to do that, let's observe that the surface of the rectangular parallelepiped actually consists of 6 surfaces, the 6 faces of the rectangular parallelepiped, which here we have denoted as S1, S2 to S6. And let us look into the equations of these surfaces. So S1, this is the surface on the xy plane. So this is nothing but z equal to 0. This z equal to 3, this we have denoted as S2. S3 is the surface on the xz plane. So it's given by y equal to 0. S4 is here given by y equal to 2. S5 is the surface at the back. So it is on the yz plane given by x equal to 0. And S6 is here, that is x equal to 1. So it's obvious that evaluating the surface integral over S means we have to evaluate the 6 surface integrals over S1, S2 to S6 and add up. So let us do that one by one. So the first one, the surface integral f dot n ds over S1. So here we put the expression for f 2x square y I plus xz square j plus 4yzk, where of course we know that I, j, k are the unit vectors in the x, y and z directions. Now, in this case, what is in the unit vector pointing outward? We can see obviously that this is the rectangular parallelepiped. So the outward pointing normal will be in this direction, which is opposite to the positive z direction. So we can say that this is nothing but minus k. So as we will perform this dot product, of course I dot k is 0, j dot k is also 0. Only the third term should remain because k dot k is 1. But now again, for the surface S1, z equal to 0. So ultimately this term also vanishes and the value of this surface integral is just 0. Let us now see what is the surface integral over S2. So we have the same function f over here, and now the outward normal points in the z direction. So this is now nothing but just k. So as we evaluate this dot product, we will get 4yz, and because z equal to 3 on S2, so this just gives us 12y ds over S2. And what is this surface element ds? Of course, this is a rectangle now, where x varies from 0 to 1 and y varies from 0 to 2. So as we evaluate this, we get the answer as 24. Let us now continue to find the other surface integrals. So the surface integral over the surface S3 now is given like this. S3 is here on the xz plane given by y equal to 0, and the outward normal is pointing opposite to the y-axis. So the unit vector n is now given by minus j. As we evaluate this dot product, we will see that I dot j and k dot j terms will vanish. So we will be left with minus the surface integral xz squared ds over S3. And this S3 is a rectangle on the xz plane where x varies from 0 to 1 and z varies from 0 to 3. So as we have put these limits and evaluate these single integrals, the answer is going to be minus 9 by 2. Let us now see the surface integral over S4. S4 is here given by y equal to 2. So the outward normal is pointing along the y-axis. So n is replaced by just j, and the surface integral becomes xz squared ds over S4. So this is now 9 by 2. Let us now find the surface integral over S5, which is the surface on the yz plane that is given by x equal to 0. The unit normal now is pointing opposite to the x-axis, so it is minus I now. Now as we evaluate this, j dot I and k dot I terms will vanish. We will be left with 2x square y. I into minus I, that gives you minus 1. But we see that x equal to 0 on S5. So therefore, this surface integral becomes just 0. And the last one to evaluate is the surface integral over S6, which is the surface x equal to 1. And now we see that the unit normal pointing outward from this surface is along the x-axis. So therefore, n is just replaced by I. And as we evaluate this dot product, we will get 2x square y ds. And since x is 1, this just gives us 2y ds to be evaluated over S6. And we see that in S6, y varies from 0 to 2 and z varies from 0 to 3. So as we evaluate these two single integrals, the answer will be 12. So now we have evaluated all the individual surface integrals, so we can now add it up to get the surface integral over S. And as we substitute the individual values we have obtained, we see that this minus 9 by 2 and plus 9 by 2 will cancel, and we will get 24 plus 12 equal to 36. And this is exactly same as we have obtained the value of this volume integral divergence if dV over V. Therefore, our Gauss's divergence theorem is verified. So with this, we will close today's session. In the next lecture session, we will take up another very important theorem, that is Stokes' theorem. So thank you and goodbye till then.